Can start the session 5 today. Hopefully you have enjoyed your breakfast this morning, and hopefully you still have energy for the second day. This morning we have 6 presentation with you have been given 15 minutes for presentation and 5 minutes Q&A. My name is Associate Professor Dr. Azmi Chakra from UPM. Will be your session chair this morning. And yeah, and when you reach 10 minutes, we will ring one, and then you only have another 5 minutes to finish up your presentation. For not further ado, I would like to call upon Mr. Asanka, who are going to present his topic, remote measurement of cardiopulmonary signal using UAV. Yeah, thank you.
Good morning, everyone. My name is Asanka Perera. I am from University of South Australia. Allow me to introduce our work on remote measurement of cardiopulmonary signal using a drone UAV. The motivation behind this work is when measuring heart rate or pulse rate, normal standard practice is using some devices which can be connected or contacted to the human skin and directly measure the readings. But this kind of technique cannot be used in situations where the reachability to the subject is difficult. So therefore, we have developed a method that can be used in situations like disaster management or war zones to identify injured or dead people, especially using heart rate and breathing rate. We call it, it's called a cardiopulmonary signal. We have used a computer vision based technique to do that. For that, we use optical properties of the skin color variation, and especially in the facial area. We exclude eye regions as well as mouth regions to remove the noises. And this technique is convenient, safe, and cost effective because it does not use additional sensors. The only sensor it uses is the camera, which is a standard device in a drone. Since this is a biomedical engineering related research, we needed ethics approval from our university. It's a standard practice of data collection from the subjects. And a total of 8 participants were involved for this research, males and females. And we used a hovering UAV, namely a 3DR solo drone with a GoPro camera. And we used 4K videos with this resolution. Because HD videos are not enough, actually we need 4K videos. And the distance was 3 meters. The distance between the hovering drone and the subject was 3 meters. And we used a pulse oximeter and respiratory belt transducer, that is simply it's a heart rate monitor and a breathing rate monitor attached to the human subject to verify our results. And we use statistical methods, namely these PCC, SEC, and this KCC and mean square errors and RMS errors as a calculating techniques. Here, I don't know if it is clear enough. This person is carrying that heart rate monitoring device with him somewhere here. That way we can verify our results. Right, and this is the workflow of the solution. The distance was 3 meters, And we use a technique called video magnification to extract the variation of colors in the human skin. And next step is a face detection step. And once the face is detected, the blind, we call it blind areas, eyes and mouth, because they add noises from blinkings as well as talking. And we divide it into 3 channels, and we use the green color channel. I will explain these steps further in the following slides. And next step is a signal decomposition and independent component analysis. Both are in time domain. Then we convert these signals into Fourier transfer, so into frequency domain using FFT. And finally, we apply some band pass filters to extract the heart rate and the breathing rates. The technique we used for the initial step was the video magnification, and it uses a 20x magnification. That means you can take it like a fast forward of a video. It's because in a normal video you can't see the color variations of the skin, but once it is video magnified, you can see the color variations from pulse rates. And we use a band pass filter. This band pass filter, here 0.15 means 0.15 beats per second. When it converts to minutes, it's 9 to 30. 9 to 30. I will explain this step later because there's a slide for it. Sorry. And the next step is the face detection, and the facial. We use the facial region, and we exclude blinking and talking by applying some mask on eyes and mouth, and we use the time domain signal for initial calculation. Next step is the signal decomposition, as I said earlier, and we use the green channel, the green component of the video signal, and then we apply a technique called empirical mode complete ensemble empirical mode decomposer, CEED, and then it decomposes the signal. That means we divide the time domain signals into various components using an inbuilt function in MATLAB for further analysis of the time domain signal. So this is the input signal, and these are the IMF, the independent components. Once it is divided into different time domain channels, sorry, time domain signals. And then we convert them into frequency domain signals. So these are time domains, these are frequency domains. So you can clearly see some noises here, as well as some good signals here with clear indications of the frequencies. With a peak means a clear indication of a frequency. And we apply independent component analysis for these good signals, that means signals with less noise. And then we convert them into FFT domain, fast Fourier transform, sorry, frequency domain using fast Fourier transform, and apply 2 band pass filters. This is for heart rate monitoring. The limits or ranges in the band pass filter is 0.5 to 3. That means when you, this is for seconds. When you multiply by 60, you get the value for per minute. That means normal the human heart rate varies between 30 to 180 beats per second. So actually it is less than that, but we have added some extra margin. And this is for breathing rate. It's between 9 to 24 per minute. And then we use a peak detection algorithm, which is altogether in MATLAB, and we count the number of peaks of the time domain signals. Once it is inverse FFT, inverse Fourier fast Fourier transform. So here in this slide, you can see the entire picture and the summary. This is time domain signal. We convert it to FFT. Then you can clearly see these two peaks belongs to one signal. This peak belongs to other signal, and we apply two band pass filters, and this correspond to breathing rate. Heart rate. This correspond into breathing rate. Then we count the peaks using a function here and here. During the experiments, all participants were asked to breathe normally, and there were two scenarios. Static scenario, that means they don't change the head, just look at the camera, just look at the drone. And the dynamic scenario, they were asked to move the head from side to side and talk and blink or smile to do some small variations in your face. But in the first step, we exclude these regions, eyes and mouth. And these are some experimental results. Using Bland-Altman algorithm. So these dots closer to zero means it's a converged result. That means the closer to the zero is better. These are for static and dynamic scenarios. And the previous one was for breathing rate. This is for heart rate. This is for breathing rates. The conclusion of this work is this technique can be applied for remote sensing assessments. For example, in war zones or in search and rescue missions, already people use drones with the thermal sensors, so IR cameras. So imagine if you want to determine if the person is dead or not. Imagine a person who just died dead. For 1.5 hours, the heat remains in his body. Or if you use a IR or thermal camera, you can't tell if he is alive or dead. So IR camera tell, okay, he's alive. So in such situation, it is important to quickly identify people who are living, who are still breathing, and to act upon them. So this technique allows us to respond very quickly for the people who are in need. And another potential application is, my professor is always talking about this one. It is to identify suicide bombers. Normally, research has showed that when someone is about to blow up himself, sometimes he's extremely calm or extremely excited. That means heart rate is not natural. So when people are queuing, so for quarantine purposes in a war zones, so if they can be identified with the heart rate, whether he's a suspect or not, so it is a life-saving application. So this is something, this is a potential application of this technique. And yes, this one. Thank you very much.
Okay, thank you, Mr. Hassan for the presentation, and also for the Q&A session from the Okay, I will ask questions. Okay, what type of the sensor that you use to measure the frequency?
It's actually the camera. The only sensor we use is camera. And
the camera, only the camera?
Only the camera. Then we use techniques to image processing techniques. So that's the uniqueness of this solution. So you use only the camera.
Normal camera.
Normal camera. It's a GoPro camera.
Okay.
GoPro Hero 4 camera. Yeah. So then we use image processing techniques to identify this region and divide the ROI of actual face region, especially the neck, forehead and cheeks.
So the camera will measure only the frequency.
Camera will record the video. That's all.
And then you take the analyze. You take the frequency of the.
Yes. After it captures the video, we take the frame, actually the sequence of images. It's actually one frame, and in that one frame, you detect the face, ROI, and you exclude the eyes and mouth regions, and these other forehead and cheeks becomes the ROI, interested area. And we apply video magnification technique to see the color gradations. Actually, when your heart is beating, because of the gas circulation of the blood, there's a difference in the skin color. Okay. Yes, you can. If you apply video magnification technique, you can clearly see this difference. But for a normal video, no, you can't see it.
So okay, meaning that what is the accuracy of it? The 3 meter, right? You say
yes,
3
distance
meters.
is 3 meters. Yes.
And need to capture the face.
Yes.
If not, then
it's not only face. Even if the hand or if neck or if any exposed part of the body is used.
And have you tested with the validate with the real situation?
Yes,
How about
yes.
the accuracy?
Yeah, actually, these are the real situations. These are our field videos. This is the first note actually on this paper, and we collected a lot of videos. And, yes.
And then what is the accuracy? It's a 90%.
Actually, okay. Yes, it's difficult to tell it as a percentage because heart rate is a range, breathing rate also range. So our results show the identified heart rate and breathing rate, they lies inside this range.
Okay. I think what you do is just to identify whether it's live or dead.
Yes, that's
whether
true.
it's live
Yes.
or dead.
Actually, the heart rate and breathing rates are only estimates, rough estimates.
Can you look at your video, sorry, your slide? Yes. With the heartbeat against there is okay, the one that reading process, the one with the uniform with the data reading process.
Okay.
After that, please.
Which one?
No, another one. Next.
Next.
Let's go into that. Okay, cool.
This one? Yeah.
Right. If you look at the figure 0.17, is that normal for that particular person, or can vary from person to person?
Yeah, actually these are some errors because we verify with because these are results from these dots correspond to the videos we analyzed, but we have the real data as well using an attached sensor for breathing rate as well as heart rate.
We do comparison.
Yes, we have.
So that 0.17, what does it show then?
Sorry.
The value 0.17.
This is the
right.
difference between
correlation
two.
or something.
Sorry, I did not.
That value that's on the right, you finally have a 0.17 or 0.22 on the graph.
This one.
I think it's an error, right?
Yes, this is errors.
That's your mean square error.
This is mean square error. This is root mean square errors.
Oh, okay.
Yes.
So that's alright.
Yeah.
So when you look at the what have you tried on infrared camera, because you can see the color contrast.
No, actually, okay. Yes, actually, this solution is only to be used with a normal camera.
So it would be black, it would have to be color.
Yes, color.
Must be color.
Yes, only RGB color images.
RGB color.
Yes.
I see. So the better the contrast, you have better result.
Yes, that's right. If it is a sunny day and you have full colors of your face, yes, it is good. Yeah, it helps.
You need better lighting as well.
Yes, better lighting. Because if you have better lighting, then you can see clearly the variations of the blood color.
You must consider about the refractance and also all the you have to do a lot of masking for the camera itself, or you do by digital?
Yeah, it's digital. Actually, it's we after you extract the RGB image, we divide it to color channels, red, green, blue, and we select only the green channel because it consists of a lot of information compared to other two. Yes, then we apply. It's in the time domain. Color channel is time domain. Then we convert it to frequency domain. Yes.
But the thing is that masking is can be a bit got a lot of noise.
Yes.
You will do a simple sensor camera.
Yes.
Right? In terms of reflectors, or there are so many variability.
Yes, that's correct.
So you zoom to the green channel.
Yes.
Or RGB.
Yes.
And then from the green channel, you extract the noise and go to your filter.
Yes, actually, okay, the noise is from different colors, maybe from the environment, from the shadows.
What is your white band noise?
Yeah, we apply band pass filters. Band pass filter. For example, sometimes normally the noise frequencies are low frequencies. When we go to frequency domain, we can clearly see some peaks.
Yeah.
Peaks means in that area the frequency measurement is high. So for that area we apply a band pass filter. That means when applied the band pass filter, we remove the noises. That means we integrate the noise frequencies.
Why that you need to go to inverse?
Yes, because we
Sorry, I think I need to stop the Q&A. I think you can have more discussion on this because of the time limit.
Okay.
Sorry about that. I think we need to have, with that, I think, thank you for the presentation.